So there are two main things that I wanted to talk about today. One was how do you solve questions involving pH, and for that we talked about two equations that are useful. One is that where exactly do we get the concept of pH from? So the idea comes from the Kc of any acid. So Kc is basically going to be, let's say I have H positive coming from HCl divided by HCl itself. And if I were to simply assume this to be a constant, considering it's a really small value in the case of HCl or a really high value in the case of weak acids, if I were to assume this as a constant, then I can simply multiply the whole thing by that and take this to be Ka. Now, let me generalize this a little bit. In any acid, I will end up with H positive ions joined with some kind of anion. So if I were to generalize this, I can say this is basically concentration of the anion that I have. And one option is that if I have the Ka or the constant for anything, I can put the value in there and just figure out H positive's concentration and A's concentration, especially in situations where I have CH3, CHH, for example, acids that give you equal moles of the negative ion and the positive ion. But even if I don't have that, even if I have something like a let's say ethane dioic acid, for example, something like this, something that breaks down in a reversible reaction and gives you COO minus and COO minus on both sides with two hydrogen ions. Even then, it's perfectly fine because I can just assume this to be X and this to be X over 2. And in the case of the first one, I can assume them to be X and X. And I can just say that the Ka is going to be X squared in the case they're equal. And I can assume Ka to be X times X over 2. And then X squared because of the H positive being squared in the case of this. And I can still plug in the values and solve this. But there is another way. And that is that we take the log and we try to introduce pH directly in there. Because to figure out the pH from this situation, I will have to first find X and then take minus log of that and then figure the answer out. But what if I take the minus log of this equation right away? So for that, what I can do is that if I take minus log on this side, I have to take the minus log on the other side. And minus log is usually represented as P. So I can call this thing pKa. And another rule of math is that just like powers add when numbers multiply, log also adds when numbers multiply. So these two numbers are multiplying, their logs will add. So I'll get up with minus log of H positive concentration plus minus log of the anions concentration. And this gives me pKa is equal to pH minus log of whatever anion I have, because we don't have a, usually these anions keep on changing, so we don't have a pH kind of thing for this. And now I can easily use this equation and directly solve for pH, especially in problems where they have given us pKa. And that is something that we use many, many times. An important understanding that you must have is that Ka kya hota hai? Just like any other constant, it is telling us the extent of the equilibrium. If it is a higher value, that means the equilibrium is going forward and favors forward. And the lower value means, like, especially the value that is less than 1, it basically tells me that the denominator side, the reactant side, wo zyada bhari hai, wo zyada heavy hai. So that means that the powers are different, or when it is towards the positive side, to mera pKa jo hoga, or when it is towards the product side, my pKa will be a small value. Just like when you have a strong acid, pH is small. And when you have a large value at the denominator for pKa, that means wo 10 power minus pata nahi kitne numbers mein chali jayegi. So the pKa will be higher. So just like pH is higher for acids that don't ionize that much or that have very low concentration of the H positive ions. क्यों? क्योंकि अगर किसी चीज में 0.0001 है तो उसका मतलब है वो 1/10 power minus 3 होगा. तो उसके अंदर माइनस लॉग करूंगा तो आंसर आएगा 3. बट अगर कोई चीज 0.1 है तो उसमें 10 power minus 1 है तो उसका माइनस लॉग लूंगा तो आएगा +1. So 0.1 is a bigger value than 0.001. But the power of 10 here is 1 minus 1 है ना, तो minus log करके plus 1 बन जाता है. And this is minus 3 multiplied by minus 1 plus 3. So pH of this situation will be 1 and of this situation will be 3, clearly telling me that the relation is reverse. So a lower pH means a higher extent of H positive, and a higher pH means the opposite. So just like that, pKa may be yahi situation hogi. So we can use this equation right away. This is also especially useful when we deal with buffer solutions, because in buffer solutions we have weak acids mixed with some salt that provides the same anion, and in those situations we might want to use the uh, an equation that quickly gives us the results without having to calculate many things or H positive separately, nikalna and all that. So one of those situations might be where you might want to use this right away. So for example, here's a question. This is an example that we talked about the other day as well. This is H2PO4 minus plus H2O, and this is going to form HPO4 2 minus plus H3O positive. Okay, so the Ka in this case, I'm going to assume water's concentration to be constant because वो बहुत ज़्यादा है. It's going to be HPO4 2 minus times H3O positive divided by H2PO4 minus. I'm assuming water to be really high. And this is a buffer solution. Ka unit would be this cancel to this. So just mole per dm. Now let's say the Ka is given to me. The Ka value at some temperature is 6.31 times 10 per minus 8. Now, what is the pH of, let's say, this is in some living cell, or मुझे उसकी pH calculate करनी है. Yeah, even if I have the pH, let's say pH is given, because blood is slightly alkaline, let's take 7 point, let's say yeah. Now, I want to figure out that what is the situation with these ions. ये किस तरह से वहां पे हैं. So let me try to see this. Since my pH is 7.4, I can either use this directly, or I can use the Ka value. I can say that, okay, minus log of H positive concentration is going to be 7.4. So H positive concentration is going to be 10 to the power minus 7.4. That's my value. Okay, so this one is 3.981 times 10 to the power minus 8. So this is the concentration that I have at the moment. Now let's say I want to figure out कि अच्छा जो ions मेरे पास बन रहे हैं उनकी आपस में ratios क्या हैं. So all I need to do is Ka over H positive. Oh, sorry, Ka is equal to H positive over H3O positive times the ion that I had over this ion. Okay, so the question says find the ratio of these two. That's pretty straightforward. 6.31 times 10 to the minus 8 over 3.981 times 10 to the power minus 8 is equal to whatever my answer is. ये इन दोनों की ratio. So that was a question that was given in the exam. Okay, so it's a pretty straightforward question कि आप Ka को कैसे use कर सकते हो और कैसे उसको use कर सकते हैं to answer many questions. And Ka and pKa, they relate just like H positive and pH relate to each other. All right, so the second part of today's lesson, where I want to finish this equilibria, that is what are partition coefficients. Again, this is a pretty simple topic in A levels. We don't go into a lot of detail of this topic. The idea is that partition coefficients are important whenever we want to extract things into one solvent and transfer them to another solvent without having to spend a lot of energy or sophisticated techniques. We just try to put two immiscible liquids together, but we have a solute that dissolves in both of them. And because of the equilibrium law, the solute travels from one immiscible solvent to another immiscible solvent. मैं आपको example देता हूँ कि let's say I have a beaker, and in this beaker I've added some water, and that water, let's say, is like this. and I've added some organic solvent, and that organic solvent is over here like this. Now they're immiscible. That's one important thing. Let me call them solvent A and solvent B, or water. Now they're immiscible, and there is some solute X which is soluble in both of them. So यहाँ पे उसकी concentration होगी X aqueous, and over here the concentration is going to be X in that solvent, whatever A is, and that's the thing. Now, according to uh, the idea, what I do is that because there's going to be an equilibrium, there's some X from here that's going to go down and dissolve in water, and there's some X in water that's going to go up and dissolve in this, and there's going to be an equilibrium in this exchange. Wherever there is exchange, there's going to be equilibrium. Whenever there is actually equilibrium, there's going to be some K. So in this case, my K is going to be called partition coefficient, that what part of this solute is dissolved in solvent A and what part is dissolved in water. So we usually keep water at the bottom of the fraction. So we say that X in A, its concentration divided by X in water's concentration is always going to reach an equilibrium. So this helps. Why? Because you can, just to ensure कि आप इसकी concentration maintain करना चाहते हो, so उससे क्या होता है कि अगर आप उसकी volume कम करोगे तो concentration same करने के लिए कुछ ना कुछ तो उसको करना पड़ेगा ना equilibrium को, and not just this concentration, वो दूसरे की ratio को same करना चाहता है. So imagine if I removed a portion of it, then the concentration has to be the same, but I've just reduced the volume. Now the concentration here is undisturbed, but the concentration here is also going to change a little bit क्योंकि मैंने कुछ mass वगैरह remove कर दिया और volume भी change कर दिया. तो अब होगा क्या? Even though the individual concentration of these two solvents remain unchanged, क्योंकि आप जितना मर्जी remove करते जाओ उसकी concentration individual को तो कोई फर्क नहीं पड़ना, लेकिन उनकी ratio हो सकता है फर्क पड़ जाए. So partition coefficient को maintain करने के लिए some solute will start to travel into this thing, or to travel into the bottom thing, just to maintain the kpc. So the rate of movement will start to change from one to another, and that is how I can use the idea of kpc to extract things from one solvent to another. If it doesn't make much sense here, let's do a couple of questions and hopefully you will understand it then. So here's a question. It says that there is a solution of 5 grams of X in 50 cm cube of water. And then we add 100 cm cube of ether. Now, clearly, ether is an organic solvent and it won't be dissolving in water. After a while, obviously, they're going to settle down and they're going to make those layers. So let's say there is 0.8 grams of X in water. What is the kpc? So let's try to see. Interestingly, it doesn't matter whether you use the units grams per dm cube or moles per dm cube or grams per centimeter cube or grams or moles per cm cube, because you're taking a ratio, the units must be consistent. And once you have them in consistency, कोई फर्क नहीं पड़ता कि आपने कौन सी unit use किया है. So I'm not going to convert it to dm cube. I'm not going to convert it to moles. I'm just going to be like, my kpc is basically the X in ether, its concentration, divided by X in aqueous solution, its concentration. And I'm using the units grams in cm cube. So initially I had 5 grams, but out of that only 0.8 remains in water. That means I have 0.8 in 50 cm cube of water and 4.2 in 100 cm cube of ether. And that is telling me what my partition coefficient is. One interesting way of solving this would be that you make the denominator same instead of putting it all in the calculator right away. What will I multiply at the bottom with to get 100? I'll just double this and this. It's a number ko koi fark nahi padega. So I'm ending up with 4.2 over 100 over 1.6 over 100. This 100 cancels out and I'm left with 4.2 over 1.6, which is 2.625. So that is my constant. And as you see, it is more than One, that's clearly telling me that the thing is more soluble in ether compared to water. And not just that, basically, what is this telling me? This is telling me that given the chance, 2.6 to 5 times more mass will dissolve in ether compared to water if the volumes are the same. And that's the main idea that Ks are important for. K allows you to compare the behavior in one solvent with the other solvent, with the reactants, with the products. सबको वो रिलेट करता है थ्रू के और आपको कंपैरिजन आसान करता है. आपको अंदाजा होता है कि रिएक्शन किस तरफ को फेवर कर रहा है और किस तरफ को फेवर नहीं कर रहा है.
Sir,
Yeah.
why did you make the volume 100?
I didn't make the volume 100. I just wanted to do some simple maths on this instead of putting double fraction in the calculator. So it's really simple. Remember the idea of equivalent fraction? मतलब मेरे पास अगर 4 over 2 है, so that is the same as 8 over 4. That's the same as 16 over 8. All I have to do is if I affect both the numerator and denominator with the same factor, so the fraction remains the same. So I'm just using that idea, the one that we study in grade 6 or 7. कि अच्छा ठीक है, मैंने इसको दोनों को अगर डबल कर दूंगा तो नीचे 100 हो जाएगा, वो 100 से कैंसिल हो जाएगा, तो मुझे कैलकुलेट करना आसान हो जाएगा. बट ऑफ कोर्स इट्स just something I am more comfortable with because मुझे mental math करना ज़्यादा आसान लगता है. Of course, you can always use a calculator and just put it all right there और आपको आंसर मिल ही जाएगा और सही आंसर मिलेगा. So here's what the goal is. We have two solutions and we have this compound. This is cyclohexanone. Okay, so cyclohexanone. This example is actually in your book as well. Okay, so I have two solutions. One is aqua solution, one is in octanol. Octanol is again an organic solvent, and the KPC is given to me. It is 2.4. Sorry, it's 24. Whoa, 24. Interesting. Okay, now they're saying that I have, so here's the situation one. We have 20 cm cube of octanol with 100 cm cube of water. And the total mass of this compound in there that we know is 2.5 grams. Okay, okay. Let's try to solve this. I have 2.5 grams. So let's say कि उसमें से X dissolves in water. ठीक है. X dissolves in water. So the K is gonna be 2.5 minus X over 100. 20 divided by X over 100. So this tells me how much is dissolved in water compared to how much is dissolved in over there. Okay. So this is going to be 24 is equal to 2.5 minus X over 20 over X over 100. Again, I'm just going to simplify this and divide this because I can. And now that gives me 24 times X over 5 is equal to 2.5 minus X over 1. Okay. So 24x over 5 is equal to 2.5 minus x. 24 over 5x plus x is equal to 2.5. This means 29 over 5x is equal to 2.5. X is 5 times 2.5, 12.5 over 29. I'll just put it in a calculator. Basically, what I try to do is that I want to keep the calculators used at the very end. मैं उससे पहले कोशिश करता हूँ कि सारा जितना मेंटली कर सकूं मैं करूं because I feel calculator slow us down. But of course, you do whatever you're comfortable with. So 0.431 grams of this have dissolved in water. So how much has dissolved in octanol? So obviously 2.5 minus 0.431. That's going to be 2.5 minus answer. That is 2.069 grams in octanol. So in octanol, you have this, and in water, you have this much. Think about it. What percentage of the substance has gone from water into the octanol? 2.069 over 2.5 into 100%. If you were somebody who wanted to make this substance move into hexanone for some reason, into the octanol for some reason, then you might want to see a better value. So this value is almost 82.8%. So almost 83%. So percentage in octanol is this. So अब आप क्या करोगे? All you need to do is take the 20 cm cube of octanol out. उसने 83% of this solution पानी में से निचोड़ के अपने पास रख लिया. तो आप वो 20 cm cube पकड़ो, उसकी distillation करो, बहुत जल्दी आप extract कर लोगे 83% of the total. And if you can afford to leave the 17% behind, that's fine. But imagine if you didn't do that. Imagine if instead of doing 20 cm cube like that, you added 10. Instead of removing 20 at once, you added 20 in there, but आपने उसमें से सिर्फ 10 को remove किया. So अब क्या होगा? Here's what's going to happen. If octanol was 10 cm cube, not 20 cm cube, here's what's going to happen. We'll do the KPC again. This is going to be, this time, let's say this is Y. So Y over 10 over 2.5 minus Y over 100. So basically what I've done is this time, I want to just directly get to how much of this is water. And notice कि वो कह रहा ये है कि KPC is 24. That means the amount or the mass that should be in the same volume of octanol should be 24 times the mass in water. तो आपने वॉल्यूम ही बहुत थोड़ी दी है, तो वो ज्यादा से ज्यादा पुश करेगा बिकॉज उसको वो 24 का बेंचमार्क अचीव करना है इक्विलिब्रियम को. सो इट विल पुश मोर इन देयर. सो लेट्स सी कितना वो पुश करता है. सो दिस 10 कैंसिल विद दिस, leaves me with y over 2.5 minus y over 10. I'll just cross multiply this here. So 24 times 2.5 minus y over 10 is equal to y. This 10 I'll multiply here. ठीक है, so 24 times 2.5 minus y equals to 10y. So 2.5 times 24 minus 24y equals to 10y. I'll bring this here. This is 34y because 24 and that add up. That leaves me with 2.5 times 24. And this 34 is going to come here and divide it. There you go. That's my answer. So I'll just put it in a calculator. So I'm getting 1.765 grams. Wow. When I had 20, I had 2.069. And with 10, half the volume, I have gotten 1.765 out. तो मैं क्या करूँगा? मैं उसमें से ऊपर वाले 10 cm cube को inject. Oh, sorry. I will just extract that part. And now what have I done? I have removed out of 2.5 grams that was originally in water. Now water has just 2.5 minus this 0.735 grams left. I am able to get 1.765 out just by taking 10 cm cube of the solvent. And remember, अभी भी मेरे पास 10 cm cube पड़ा हुआ है क्योंकि मैंने तो 20 की बजाय 10 यूज किया ना. What is the percentage here? This is 1.765 divided by 2.5. That is almost 70.1%, 70.6%. So 71% तो हमने यहीं पे निकाल लिया. उसमें हमारे 83% निकला था. Now let's try again. Now this time I still have 100 cm cube of water. I still have 100 cm cube of water. And there is 0.735 grams in 100 cm cube of water. And now I add another 10 cm cube here. So obviously there's going to be an equilibrium going to be established again. This is going to move here. So let's say this time I get Z in here, Z of this in here. So obviously 0.735 minus Z is left over in water. So let's see, अब अगली दफा कितना उसमें रहता है. तो KPC is going to be Z over 10 over 0.735 minus Z over 100. Again, we do some maths. That 24 times 0.735 minus Z over 10 is equal to Z. I will again get 0.735 times 24 is equal to 34 Z. So Z will again come out to be this over 34. And my value is 0.519 grams. देखने में तो लग रहा है बहुत छोटी value आई है, but let's see. Now I will simply remove this much again and I have been able to extract 0.519. So let's see total कितना निकाला मैंने. First time I was able to get 1.765 with the first 10 cm cube. And now I'm able to get 0.519 grams. How much is that total? That is 2.284 or 2.28 कर लेते हैं. out of 2.5. What percentage is that? 91.4%. Wow. Just by making the process a little more tedious, instead of getting 20 cm cube, we have done it in 10 and 10. पहले 10 किया, उसका इक्विलिब्रियम एस्टैब्लिश किया, उसमें जितना वो डिसॉल्व होया उसको निकाल लिया, और फिर another 10, और फिर उसमें जितना डिसॉल्व होया उसको निकाल लिया. Because the KPC needed to be established, the equilibrium had this urge to manage or to match the KPC somehow. कि उसने हर सूरत में 24 times mass in the equal amount of of octanol dissolve करना ही करना था. I was able to exploit it. और मैंने कम वॉल्यूम में काफी ज्यादा mass निकाल के I was able to extract a 91% success in this. And by the way, if I divided it instead of 10-10, imagine if I did 5-5. Of course, that will make it kind of difficult for me to practically do it क्योंकि काफी time लग जाएगा. And if I have the gift of time and I can do it, then I will get even better results. कि मैं पहले first 5 cm cube ऐड करूंगा, उसको extract करूंगा, फिर another 5 cm cube ऐड करूंगा. Of course, practically इसको करने में challenges आएंगे. 5 cm cube is a really really small value. और उसके साथ जब आप उसको extract कर रहे हो pipette से, तो उसमें हो सकता है आप पानी भी निकाल लो साथ में, और आपको some challenges with respect to the success in distillation भी face करने पड़ेंगे. But you will still get better of that substance out. And all of this might not be a very good application of this, by the way. Because अगर आपको वो substance को निकालना ही था, तो why not just evaporate the water in the first place? और आप 100% 2.5 grams पूरे का पूरा निकाल लो उसमें से. But that is a valid point. So why do we do this? We do it because there are situations where we are not able to get the water out. Imagine if you wanted to extract some oil, some pollutant that was dissolved in a lake or in a pond. और उस pollutant को निकालने के लिए, what you can do is you can have a layer of some organic substance that you can extract without harming the environment. You will be able to clean that pond to a much, much better extent by this. So it's kind of like having a sponge that absorbs the solute from a solvent or from a solution. So in that thing, this will make sense. In a lab situation, this might not make sense. But the principle is there, and the KPC will come to our advantage over there. Okay.